Okay, so welcome to lecture 8 of week 4. So what we discussed in the last class was the entropy of mixing for two atomistic solvents. Basically, what was done is space was discretized into a lattice, and this is basically the slide, exactly the slide from the last class. And basically, the number of ways to arrange A and B identical molecules was written as Na plus Nb, where Na was the number of A molecules, Nb was the number of B molecules, where B would be the solvent. Upon if they're identical particles, Na factorial and Nb factorial, because you can interchange the position of all the A particles between themselves, and you can't figure out any difference, right? And then basically the entropy was calculated as S mix to Kb, and the log of this previous expression was taken, and we used Stirling's approximation. And as a consequence, doing a bit of algebra, we got S mix was equal to minus Kb Na ln Na by Nb, the volume fraction, plus Nb ln Nb plus Na plus Nb, which was could be written as the volume fraction. And remember that basically this is less than 1 and this is less than 1, so ln of this quantity will be negative, right? And from here, this is the most general expression. And from here, we in the last class, we went for dilute solution and calculated the osmotic pressure and so on and so forth. And realized that osmotic pressure, the origin of osmotic pressure is entropic is in origin. But today we are going to look at cases where it is not dilute, and it's not only a polymer, it's not just a solution of atomistic particles, but one of the particles, suppose A, could be polymer chains, and right, and that comes within the purview of Flory Huggins theory. So now suppose you have a polymer chain with n monomers, capital N monomers, and the question is, what is S mix, the entropy of mixing? And we have assumed that A and B, the solvent particles, and A, the monomers of a polymer chain with n monomers, they occupy the same unit volume in configuration space. And one could write the volume fractions. If one assumes that, one can write the volume fractions of the two components as phi A equal to A, the volume occupied by A molecules, upon the total volume, which is Va plus Vb, and this can be written as V0, basically the volume of one lattice unit, into number of A particles into V0 Na plus Nb, because we have assumed that A and B uh, entities occupy the same unit volume in configuration space. And basically then cancelling V0 out from the numerator and the denominator, you can see that Na upon Na plus Nb is the same as the volume fraction of A. And similarly, phi B, the volume fraction for the B molecule, can be written as Nb upon Na plus Nb molecule, right? Assuming this. Na plus Nb is the total number of lattice points, the total number of particles, if you like. And basically, this came from, and phi A plus phi B is equal to 1, the total volume fraction, of course. I mean, sum of the two volume fractions has to be 1, right? And so now uh, the total number of lattice points occupied by A particles is written as Na, and that is equal to the volume fraction into the total number of lattice points, right? And similarly, NB can be written as the volume fraction of B into total number of lattice points, because n the small n is Na plus Nb, right? So S mix, the entropy of mixing, finally the most general expression can be written as minus Kb. So this is, I've just copied the previous term which you already saw in 2 slides before this, and this is now converted into phi a, right? And this expression is now converted into phi b, right? And now substituting these expressions here, we are writing n capital Na to be n into phi a, and this to be n into phi b. As a consequence, you get S mix, entropy of mixing, equal to minus Kb n, total number of lattice points, into phi a ln phi a plus phi b ln phi b. And if you want to calculate the entropy of mixing per lattice point or per particle, then it is minus Kb phi a ln phi a plus phi b ln phi b. And this is, if you see expression somewhere in the free energy, phi a ln phi a plus phi b ln phi b, you should immediately click to you that this is the general form of expression for entropy of mixing, right? So this is the expression for entropy of mixing per particle. So any entropy terms of mixing is written in this form, and this is often what you see in papers, and this is the starting point of various investigations in the future. So what you are learning is basically the standard language in which some of the polymer physics is talked about, whether it be theory or the experiments. And many of the quantities we are discussing in these classes are actually measured in experiments. Yes, we have not talked about the experimental techniques, but this is the broad language in which people talk, right? Okay. So now the question is, now suppose if all the Na particles, points, are not independent of each other and they are constrained to move as a group, as in a polymer chain with n monomers of a polymer, right? Then the number of independent entities that can be exchanged in configuration space is not in free. You cannot simply replace any particles with itself. Rather, you have to move as a group, right? So n particles have to move as a group, and you can interchange n particles with a group of another n particles, capital N particles. As a consequence, the entropy of mixing becomes minus Kb Na by n. This is the basically degree of freedom, into ln phi a plus Nb ln phi b, where Na by n is essentially the number of polymers. Now, what you can interchange between positions is not a single particle Na, but a whole polymer, and each polymer has n monomers and degrees of freedom, if you like, right? Well, they are constrained to be together, so you can move now n a particles and exchange, and then you will get the same state, right? I mean, same configuration state or same microstate, if you like. So when you have Na polymers, uh, small n a polymers, and capital Nb solvent, then the expression for the omega will be Na, because now you can interchange only entire polymers with capital N monomers per polymer. So degree of freedom is thereby, I mean, as per this theory, a bit reduced. So the omega will be the small Na plus capital Nb factorial upon small na factorial, and capital NB factorial. As a consequence, S mix, just like in the previous case, will have nearly the similar expression, except that capital Na will now be replaced by small n A, which is the number of polymers and not number of monomers anymore. And similarly here in the numerator, again you have small n A by small n A plus NB, and this term remains intact. But if you want to convert this thing to volume fractions, we must remember that small n A polymers with n monomers occupy the volume equivalent to that of basically Na monomers, right? Sorry, there should be an A here. So the number of monomers in will be still n into n A, which is capital N A, which is the same as previously. So when you convert this fraction into volume fraction, you get this still to be phi A. But this prefactor, small n A, is this capital Na by n. Okay, and this term of course remains intact unless this itself is made up of polymers. So note in this calculation what have been the assumptions. We are ignoring any internal degrees of freedom within the monomer. So suppose the monomer has carbon, hydrogen, or different other chemical units which can rotate and so on and so forth. So we are neglecting all of that in this coarse grain model. So we are just, if you like, considering only translational entropy. So we are just saying we are considering only the position of the entire monomer. Moreover, we have been considering when we are replacing, uh, we are putting constraints so that you can exchange the position of an entire polymer, each with capital N monomers. Then you are considering only the translational entropy of the position of the center of mass of the polymer. That is the one which is being considered, and we are not, or we are ignoring the conformational entropy of a polymer chain. So that is not being accounted for. You are saying that, okay, the polymer as a whole is a unit, and that you are interchanging positions of entire polymers, right? And of course, we are also neglecting conformational entropy. I mean, since we are anyway ignoring conformational entropy, we are not considering the effects of conformational entropy due to solvent monomer interactions. I mean, sometimes it could be ideal chain or extended chain. So those correction we are not considering in this calculation. Moreover, we are ignoring volume change of solution due to mixing. So these are the assumptions which are going in for the simplification of things, right? Now let's go further ahead. The entropy of mixing is minus Kb Na, total number of A particles, by N. So this quantity is number of polymers into ln phi A plus Nb into ln phi B, right? And this in turn can be written as basically I'm replacing Na in terms of N into phi A. So this in turn can be written as Kb n phi A by N ln phi A and phi B into ln phi B. And for polymer solution, so this is basically a polymer solution because you have long chain molecules of A with n monomers per chain, but you're considering a atomistic solvent. I mean, all right. So the total entropy per site, where small n is the total number of lattice sites, is then minus Kb phi A capital phi A by n number of monomers ln phi A plus phi B ln phi B. It is an important result which we'll be using. Moreover, if n A polymers, so this is small n, are in a solvent of a polymer chain. So basically this itself, B itself, is not an atomistic solvent or a molecular solvent. but it consists of polymer chains themselves, right? So that the solvent polymer has ns monomers per chain. Then the entropy expression, entropy per lattice site, becomes minus kb phi by n ln phi a plus phi b plus ns. Ns is the number of monomers in the solvent polymers chain. This is called a polymer blend into ln phi b, right? So this is basically what is the entropy of mixing. To have a slight idea of the numbers, so this is so basically what I'm calculating is S mix equal to this n is coming on this right hand side of the equation. So just to give you an idea of numbers, that when you have polymer chains, the entropy of mixing drops drastically. What you could do is explicitly take 50 black balls and 50 white balls, right? I mean, suppose, so 50 black balls or 50 white balls essentially consists of phi a, the volume fraction, to be half, 50 by 100, and phi b equal to 50 by 100, right? And if you mix them all over, and if you have a molecular solvent, I mean, I shouldn't use the word atomistic solvent, I should use the word molecular solvent. So each of these Na particles can move freely and independently of each other. You don't have a polymer chain. Then if you put in numbers, where this small n will be 100, then the entropy of mixing would be 0.69. And this is taken from Rubinstein and Colby, page 139, figure 4.2, as you can just see. Now, if one of the components was a polymer chain of length, suppose 10 monomers, right? So you have 5 chains, and each chain has 10 monomers. So 5 10-ball black chains and 50 white balls, which is basically polymer in a solvent. Then you can calculate the entropy of mixing, and that is 0.38, right? This is basically S mix by Kb. So I should have written S mix by Kb. So I'm just calculating n phi a ln phi a plus phi b ln phi b, basically that term. And however, if this entire lattice was filled with a polymer blend, where both the polymer chain, the black chain had 5 monomers, 5 polymers, each with 10 monomers, and the solvent was also another set of polymers, uh, which you have 5 polymers, each with 10 monomers. Then you're just using this expression. So n will be 10 and ns will be 10 as well. The entropy of mixing is 0.069, right? So it drastically drops. The entropy of mixing contribution to mixing drops drastically if you have long chain molecules. So this is the basic message which I want you to take on. And this doesn't take in configurational entropy, as I mentioned, right? So it's very important to remember also the approximations which are going into the theory. Okay. So, but you know, a system which, whether it will mix or not, it will depend upon the free energy minimization. And the free energy minimization consists of energy terms and entropy terms. What we have calculated till now is just the entropy terms within certain approximations. And now what we are going to do is calculate the energy of binary mixing. But here we're going to not keep the previous assumption that we are taking dilute solutions, We are going to consider AA interactions, BB interactions, and AB interactions. Remember, in the previous class, we were talking about the dilute solution where we only considered that A particles were surrounded only by B particles, or A was surrounded by water particles, and we considered only that interaction, right? And BB interaction was subsumed, or basically put into the chemical potential for the water molecules. But here we are not doing such assumptions. We are writing down where we shall consider the energy of interaction for AA terms, AB terms, and BB terms, and then calculate the free energy. Uh, the other thing I want you to note is that entropy always promotes mixing. If there is mixing, there will be a net entropy gain, right? Minus kb into a negative number, so there will be an entropy gain. So entropy always promotes mixing, whereas the energy term the energy of mixing can be either negative. In that case, the free energy would be further minimized. It will further decrease, and that promotes mixing. Or the energy term could be positive, and then it could be uh, opposing mixing. So a competition between the energy terms and the entropy terms will decide what the equilibrium state will be, whether it will be an unmixed state uh, or it will be a mixed state, right? So when you consider the free energy for polymers, uh, considering energy terms and entropy terms, it is called the Flory Huggins theory. And Flory Huggins theory is typically done at constant volume because we are ignoring any volume change on mixing. So we shall be dealing with Helmholtz free energy, and that is what is relevant at constant volume. The other thing to remember is that Flory Huggins theory is a mean field theory. What is a mean field theory? The fourth year students might know, but for the third year students, I shall emphasize how we are taking averages. We'll be considering the average interaction of particle A and particle B, and we avoid fluctuation calculations. Right. So the why is it mean field? It will become clear as we go through the lecture. Now, remember, I mean, in general, an A particle could be surrounded by, suppose, three B particles and an A particle in a particular configuration. But if this happens in general, that A particles are in generally, surrounded with a larger number of B particles, then you are considering higher concentrations of B typically, right? But even if you have higher concentrations of B in a solution, uh, while this will be the generic case, suppose you have a 75%, the 5B is suppose 75.75. 75% of the solution. Then in general, this you will have three B particles and one A neighboring particles, but you will also have cases where you have only two B particles and instead you have two A particles, or there can be statistically the possibility that an A particle is surrounded by four A particles, and there are higher density of B at some other positions, right? So there will be fluctuations in concentration, right? But you'll see that in the mean field theory, or the so-called Flory Huggins theory, those will be ignored. Now, on an average, if you have basically uh, two A particles, sorry, I wanted to draw one more A particle. Suppose these two are A and these two are B, then you would have a medium concentration of B on an average. And for low concentration of B, you would have on an average, an A particle will be surrounded by, say, three A particles and one B particle. But of course, for fluctuations, even in this case, you could have an A particle which is surrounded by two B particles and two A particles. But those those fluctuations will be neglected in a mean field, in an average. We'll be looking at average concentrations, mean concentration. So we are doing essentially a mean field theory, and this will be more clear in this. So basically what we are going to say in the mean field theory, while calculating the energetics of mixing, that the probability that a particle A is a neighbor of another particle A is dependent on the mean concentration of A in the solution, that is equal to phi A. Okay, if phi A is higher, then the probability that particle A will be surrounded by other A particles, of course, will be higher. But we'll say that it is generally for all lattice sites on an average, the probability that a particle will be surrounded by another A particle, that is dependent on phi A, and the number of A neighbors, right, is basically will be multiplied by the coordination number, or the number of neighbors into phi A. Okay. Similarly, the probability that a B particle is a neighbor of another B particle is dependent on the mean concentration of B in solution, which is phi B. Here we were considering again the mean concentration of A in the solution, which is phi A, and again the probability of B that it is a neighbor of another B particle is basically dependent on phi B, which is the mean concentration, right? And if you multiply that by the number of neighbors allowed, that will give you the total number of A neighbors of A and the total number of B neighbors of B, right? And similarly, the probability that the B particle is a neighbor of A is dependent on the mean concentration, again phi B, right? So this is again an approximation, fluctuations ignored. So for one A particle, suppose there's a one A particle, the mean energy of interaction will be UAA. I mean, suppose there's an AA particle, there's an A particle, and just next to it is another A particle, then the interaction energy is UAA. So for one particle, the interaction energy will be UAA into the probability that the probability that you have an A particle as its neighbors plus UAB, suppose A has a B neighbor, into phi B into Z neighbors, right? Because if you multiply, you get the number of neighbors, number of A particles and number of B particles. Right. Similarly, for a B particle, the mean energy of interaction, so we are looking at one B particle, the mean energy of interaction will be UB, which is equal to UBB. Suppose a B has another neighbor B, then UBB, the energy of interaction of such a case, into phi B into UAB into phi A into Z neighbors, because if you multiply by Z neighbors, Z is the allowed number of neighbors. Suppose this is A, right? Surrounded by 4 B particles on an average and 2 A particles, right? Then there will be basically AA interaction here, and 4 BB interactions. So phi A into Z neighbors would exactly give that, and similarly phi B into Z neighbors will exactly give the number of such pairs. And this is the energy of interaction for one particle. So one particle surrounded by so many neighbors. Z is equal to 6 in this case, right? Where Z is called the coordination number or the number of neighbors of a particle. Okay, so now this was for one particle, right? But the number of A particles in the solution is n into phi A, and the number of B particles in solution is n into phi B, in which I have written as phi B, I have written as 1 minus phi A, right? So the interaction energy for the whole lattice is the number of A particles into number of AA interactions. What was the number of interactions for one particle? It was UAA into phi A into Z, right? Plus number of B particles into number of BB interactions. And what was number of BB interactions? It was for one particle, UB, I mean, the number of BB interactions was UBB into phi B into Z. That's the number on an average. Each B particle has phi B into Z number of B neighbors into UBB. So take this picture, right? So the interaction energy for the whole lattice is number of A particles into number of AA interactions, number of B particles into number of BB interactions, number of A particles into number of AB interactions, and number of B particles into number of AB interactions. But we must avoid double counting, because if we are considering this particle, suppose, is a neighbor of this particle, right? That's one interaction. Later, since you are counting the number of A particles, you are also considering this to be the central particle and this to be the neighbor, right? So you're going, if you use just this formula, this expression, you're double counting. Similarly, for AB interactions and BA interactions, you're double counting. So there's a factor of half here. So number of A particles is N phi A. This is the interaction energy number of AA interactions for each particle, and phi B, number of B into number of BB interactions for each particle, and similarly these two terms, right? And then this can be, if we do a bit of algebra, it can be written as Z, the number of neighbors, into N, the number of particles in the lattice, avoiding double counting, into UAA into phi A whole square plus 2 into UAB phi A into phi B, and phi B has been written as 1 minus phi A, plus UPB into phi B whole square, which has been written as 1 minus phi A is missing here, whole square, right? So this is the energy of interaction when things are in a mixed state, when A has a large number of B neighbors and B has a large number of A neighbors, depending upon the volume fraction of phi A and phi B. But if you want to calculate, so this is the interaction energy for the mixed state, but if you want to calculate the change in interaction energy, you need to calculate the energy before mixing. And before mixing, each A particle, so suppose you have a box and this side is A and this side is B, and here in this side all A particles are surrounded by all other A particles, and what is the energy of enthalpic energy, the actual interaction energy of such a case? And each particle A, so for one particle, the interaction energy is Z, the number of neighbors, in this case 6, by 2, because to avoid double counting, into UAA, right? UAA is the interaction energy between AA particles. And similarly, in the unmixed case, the energy of interaction for UBB is, sorry, I think I've used a bad notation. I should have just said some other symbol. I should use simply some other symbol. But I want to say that for this B particle, the interaction energy with these 6 other B particles, Z other B particles, is Z by 2 to prevent double counting into UBB, which is that, yeah. Just take this to be capital U and this to be small u, Okay, so here one can't make a difference, but this is capital U, and this is capital U, this is small u, and this is small u. Sorry. So total energy of the total energy for A particles, and how many A particles are there? N into phi A is the number of A particles into the interaction energy for each of the A particles is N phi A into Z by 2 UAA. This UAA is here, right? And similarly, N phi B, the number of B particles into Z by 2 into UBB. This is this UBB setting here, right? And then the energy of the N mixed state is Z N by 2 UAA phi A, right? This is the volume fraction of A plus UBB 1 minus phi A. What have we ignored? We have ignored any AB interaction. Where will there be AB interaction? Only at the interfaces. So you have a box like this. Here, this is full of A particles and this is full of B particles. There will be an interface where the A particles and the boundary between A and B particles, right? So there will be some particles at the boundary, and then some unmixed state, and on this side there is A, and on this side there is B, and there will be AB interactions, or rather UAB interactions here. But compared to the bulk, especially when you take a large number of A molecules and large number of B molecules, the number of molecules in this interface at the surface will be significantly less than the number of particles in bulk, right? Because the area goes as L being the dimension of the box, L square. So number of such interactions will be, suppose, epsilon AB into X, right? And the number of interactions in the bulk will be some other epsilon into N cube. So number of interactions, the bulk interactions will dominate over the surface interactions, and we have ignored the energy of interface, as the number of AB interactions is much less compared to the number of AA interactions and BB interactions, or number of bulk interactions. So the interaction energy change, the internal energy change due to mixing is U mixed minus U unmixed. Okay, and when you write down, so this is the one for unmixed. This was the energy of interaction for mixed, and previously we had also calculated entropy of mixing, right? Entropy of mixing in the unmixed state, the number of microstates is only one. On one side you have A, and on the other side you have B, right? So you don't have to calculate the entropy in the unmixed state. You have to only calculate the energetics in the unmixed state and in the mixed state, right? So anyway, just to give you the big picture. So the internal energy of mixing is U mixed minus U unmixed. And if you put in all the terms and do a bit of algebra, basically rearrange terms, cancel terms, and so on and so forth, what you will get is Z, number of neighbors, N, the total number of particles in the lattice, by 2 to avoid double counting, phi 1 minus phi A, which is phi B, the number of it is basically number of basically the volume fraction of B molecules into phi A into 2 into UAA minus 2U, sorry, minus 2UAB minus 2UAA. These were capital U's, and these are small u. So this u is the energy of interaction between a molecule and another a molecule, right? So by the way, so is this one. Sorry, this is not capital. This is also small u. I'm sorry for this. Yeah. So this is small u, A interaction, AB interaction. This is AA interaction, two particles, two molecules, and this is BB interaction. So this is what you get, right? And if you like, the energy of mixing per particle, small n, can be written, introduce a kBt here and a kBt in the denominator, and this entire quantity, the energetics of individual pair interaction, these are the energetics of pair interactions by kBt, is called the Flory interaction parameter. Now this is the quantity which is determined experimentally, and when you are discussing the phase diagram of polymer solutions, of course that's just the beginning, and then you go on and look at many other things, but this is the beginning. So basically you talk about the Flory interaction parameter, right? The energy of mixing can be written as kBt. Chi already has kBt in the denominator. These are the pairwise interaction terms, right? Into phi a into 1 minus phi a. 1 minus phi a is nothing but phi b. So the total free energy of mixing per particle, or the change in free energy due to mixing per particle, is delta U mix by N minus T delta S mix by N, and then the expression comes as kBt. T is there here, Kb was already there, phi A by N, number of monomers in a polymer chain, ln phi A plus 1 minus phi A by Ns, number of molecules, number of monomers in the solvent chain, ln 1 minus phi A. So these are the entropic terms. As I said, phi ln 1 minus phi b ln phi b, they are always entropic terms. Ln phi a is negative because phi a will be always less than 1, and this is the energetic term. And this is a very common occurrence as the starting point of various studies whenever you're talking about phase diagrams and mixing and polymer solutions and so on and so forth. And of course, you will have other complications. Suppose this is the energetics of mixing and the entropy of mixing, and then you could have charge of the system, or you could have other properties, maybe architecture, etc. So then you would have other terms which would contribute to the free energy. Here we are considering simple linear polymer chains, and this is a very frequently occurring expression when you study advanced papers on polymers. And for mass polymers, proteins, DNA, other complicated stuff are all polymers. But of course, if you have a DNA, then you have to consider charge as well. We have not considered charged interactions here, right? And if there is substructure, or it's not a linear polymer chain, then there will be corrections to these terms. So this is just for a linear polymer chain, and this is the so-called free energy, or the change in free energy for mixing, and this is called the Flory Huggins equation. Now, if Ns, this Ns is 1, then you would call it a polymer solution. I've written down the most general case, this like for a polymer blend. And if this N equal to 1 and this Ns equal to 1, then that's the free energy of mixing for a regular solution. Okay. Uh, the other thing I would like to say, well, I'm just, I think, repeating it. If chi phi a into 1 minus phi a is positive, that is, see, this is the positive quantity, it's a volume fraction. This is a positive quantity, it's a volume fraction. So chi is positive, then it would oppose mixing because this term would increase the free energy. Right, this is the energetics of mixing. Right, so if this quantity is positive, the energetics of mixing is positive, then it would oppose mixing. Now, if chi is equal to 0, it is called an ideal mixture, and if chi is negative, it is always promoting mixing. Now, if chi is negative and the entropic terms are anyway negative, so and entropic terms is anyway always promotes mixing. So if chi is negative, you'll find the A and B always in a mixed state. It's in a homogeneous state. So basically A is always floating around mixed up and the solvent, whether it be a polymeric solvent or a regular solvent, it's always in a mixed state. However, in practice, what you often find is that there's a net repulsion between species. That means if A and B are close to each other, there's a higher energy cost, or there's a net energy cost compared to if A particles are close to each other or BB particles are close to each other. Right? So there's an energy cost of AB. There's a consequence UAB is large and positive value compared to the other two values, and chi is positive. That means sometimes you will get mixing and sometimes you won't get mixing. So whether the polymer will mix or not will depend upon the value of phi, because the entropic terms will promote mixing. Chi into these terms will try to, if chi is positive, it will uh, try to avoid mixing. And then you have to calculate the entropic terms and the interaction terms and figure out whether the system, and that will be decided upon the value of phi, of course. Uh, basically, basically, yeah. So that will decide whether a particular polymer, depending upon its interaction with the solvent, and for different solvent molecules, this UAA, UBB, and UAB are going to be different, and correspondingly chi values are going to be different for different solutions, for different microscopic energetics. Chi will be different. So whether a thing will mix or not will depend upon the chi value and the phi value, the volume fraction, because that will determine both this term and also the entropy of mixing. Okay, so this is the basic formalism in which things are taught. Of course, there's a mean field theory, but this mean field theory, while it's being simple, gives a hugely important understanding of, or a general language to talk about polymer solutions. Of course, you have more accurate theories with lot more details, correlations, and then you have many more free parameters. It becomes extremely complicated when you relax those assumptions. Yes, those equations are there, and if you want very detailed calculations and match with experiments, those are important. But this framework already gives a good understanding when a thing will mix, not mix. You typically, experimenters love to talk about the chi parameter, and or when you want to do a modeling or understand in the simple language, not extremely detailed, you would want to talk about this chi parameter, Flory interaction parameter. Much of those approximations actually are in the chi parameter, and in practice chi is often written as A plus B by T, and this, remember, this is a temperature dependent quantity, so the chi itself can change uh, depending upon the temperature A, can be positive or negative depending upon what polymers you have, and but those are all subsumed in that. Okay, so with this, I shall come to the end of the lecture. This is already 8 classes, and I understand that I've covered quite a bit. All this can be found in also Rubinstein and Colby, chapter number 4, parts of it. What we haven't talked about at all is polymer dynamics, because often the dynamics of how a DNA or I mean, basically, whenever you also want to know how a polymer relaxes and how it relaxes, how it changes, how various patterns and structures are formed in soft matter. Here we have basically talked about equilibrium. We have not talked at all about uh, how some pattern will change or the polymer will relax or it will change. And I wanted to have a lecture. Maybe I will add one more lecture, but you won't have that in your exam. So it's here that we will end. Okay, thanks.